Hello and welcome to today's Battery Insights session. In my last session of Series 1, Part 1, I covered four topics. The first topic was an introduction to the world of batteries. The second topic was a brief history of lead acid batteries. The third topic, which I covered, was the subsequent developments which took place in the lead acid battery industry. And the last topic that I covered was the various applications of batteries. And today I am going to part 2 of this series 1 of my introduction of lead acid batteries to you. So let's proceed to the next slide to continue with part 2 of the series. Today we will cover the construction of lead acid batteries, the typical performance characteristics of the batteries, and the performance of batteries when they are connected in series and parallel. When it comes to construction, the two primary raw materials required are lead alloy to make the grid and lead oxide, which serves as the active material. There are, of course, certain other materials that are required, such as containers, covers, and separators. We will address that later, but let me begin with the alloy. When discussing lead alloys, the type of alloy used depends on the application of the battery and the specific type of battery. Now, alloys are mainly used to cast grids. The grids are the current conducting structures and they are cast to hold the active material. In pasted plate batteries, they are of the mesh type, and for tubular plate batteries, the positive grids have a spine structure. When it comes to low maintenance lead acid batteries, which are of the flooded type, we have lead alloy that contains antimony, arsenic, copper, tin, and selenium. The reduction of antimony content is possible because we use selenium as a grain refiner, which aids in the casting of the grids. In a low maintenance battery alloy containing selenium, the reduced antimony content results in less gassing. Naturally, this results in a lower requirement for topping up with water. The frequency of topping up is reduced, allowing you to top up the battery after a relatively longer period. This type of alloy is used in the manufacture of maintenance-free motorcycle batteries and automotive batteries. They are also used in industrial applications such as stationary batteries for standby purposes, telecom applications, and railway applications. Now let's move on to the next type of battery, which is the sealed maintenance-free battery known as SMF batteries or VRLA batteries, which is specifically valve regulated lead acid batteries. So these batteries are also known as SMF, that is sealed maintenance free, and they are also known at times or referred to at times as VRLA, that is valve regulated lead acid batteries. In these batteries, there is no possibility of topping up with water throughout the battery's entire life. The vent plugs are sealed, preventing any maintenance. In such batteries which are used for motorcycles, automotive applications, and sometimes for stationary applications in standby purposes or for telecom or railway applications, we use an alloy with absolutely no antimony. This lead alloy contains calcium, aluminium, tin, and sometimes silver. I have recorded and relayed a podcast on the ideal composition of calcium, aluminium, tin, and silver. Generally, the positive grids are composed of a different material and the negative grids are composed of a different material. At times, people use a hybrid alloy in maintenance-free batteries where they sometimes use the lead selenium alloy for one electrode and the lead calcium alloy for the other electrode. Now, Let us proceed to the next slide. Here I will discuss battery alloys for cycling batteries. Cycling batteries are batteries used every day to achieve a depth of discharge of 80% or in some instances 70% depth of discharge as allowed by the manufacturer. These batteries are used for electric motorcycles, e-rickshaws, scrubbers, sweepers, golf carts, and also in traction batteries which are used for material handling equipment applications. Here the antimony content is relatively higher because we want a better charge acceptance as well as corrosion resistance. After all, these batteries are charged and discharged daily. As I mentioned, the alloy is used to make the grid, whereas the active material is lead suboxide. Now let us see the function of lead suboxide. Lead suboxide, as I mentioned, is the active material which takes part in the reaction. In the case of pasted plate batteries, which are typically used in automotive applications, both the positive and negative plates are pasted type. The same applies to motorcycle grids. In the case of industrial batteries, where tubular plates are used for the positives, the negative is still of the pasted type. In all these cases, lead suboxide is mixed with certain chemicals such as barium sulfate, carbon, fiber, venispers, or lignin. People use graphite and nanocarbons, and depending on the manufacturer's requirements, the quantities, chemical composition, and specifications of the material varies. These chemicals are mixed with water and subsequently with acid, forming a paste that is then applied to the grid. A pasted plate is then made. Now, when it comes to a tubular plate, lead oxide is usually mixed with red lead. The quantity of red lead may vary. It may be nil or 25%, 50%, or in some instances, 100% red lead is also used. Of course, quantities in between, like 33% red lead or 40% red lead, is also used. But generally, the quantity of red lead is lesser than lead suboxide, except in cases where uh, the red lead goes up to 100% for some batteries. Tubular plates are manufactured by filling the tubes with a powder, paste, or slurry. These are the three methods by which tubular plates are manufactured, and this is how an industrial tubular positive plate is made. I shall now show you how a pasted plate looks and how a positive tubular plate looks in my next slide. Here you see the grids of the mesh type are shown on the left hand side. These are different designs of grids. Once the pasted plates are formed, they acquire a chocolate brown color in the case of positives and a slate gray color for negatives. You have the positive plate pasted and the negative plate pasted and formed in the center of the slide. When I say formed, I mean they are already charged. After the pasting, a current is passed and these plates are already charged, which means they are formed from lead sulfate to PbO2 in the case of positives and lead sulfate to negative Pb in the case of negatives. These plates are the ones which are used in automotive or pasted stationary batteries as well as motorcycle batteries. On the right side, you see a positive plate of the tubular kind, and the negative plate, of course, is again pasted. These are the plates used in the production of industrial batteries. Once these plates are made and a group is formed, we need to separate the non-conducting elements, so we have something known as separators. Let me show you these separators, an essential component of lead acid batteries, in the next slide. Previously, PVC separators were commonly used. However, of late, polyethylene or PE separators are the most popular choice. These PE separators come in a rolled form, allowing you to create a sleeve or pouch pocket for the battery plates. PE separators have a better resistance to high temperature operation, and they are not brittle, unlike the PVC separators, which sometimes have been found to be too brittle and difficult to handle in the production process. Let's proceed to the next slide. For a more precise understanding, you can refer to this schematic representation of the battery. This is a sort of cut section of the battery which is displayed. On the extreme left of the left slide, you see a grid followed by a brownish positive plate and then a separator. The arrangement next to the grid shows you a positive plate, a separator, and a negative plate. These plates are arranged alternately. You can see that the lugs are positioned on either side and then a group is formed. Once the separators have been inserted, the group is placed into each of the compartments. The compartments are within the container and there are 5 partitions and 6 compartments in this case. The group is put into each of the compartments and we typically interpartition weld these cells together in a series formation and then remove the terminals at both the ends. As you can see, there is a positive terminal and a negative terminal. In this diagram, you can see that the groups are housed in a 12-volt battery container. The nominal voltage is 12 volts and there are 6 cells. Let me now show you the battery containers. These are the battery containers. On the left side, you see the containers that are all of 12 volts. That is, they have 5 partitions with 6 compartments. On the right side, you see the larger containers. These individual containers are rated at 2 volts each and are used mainly for industrial application batteries, specifically for stationary batteries, and similar containers are used for traction batteries too. When it comes to industrial golf carts, scrubbers or sweepers, monoblock containers are used, similar to the ones used in automotive industry. However, these industrial batteries are typically made in a 6 volt and 8 volt configuration. When they are sometimes made in a 12 volt configuration also, the containers may not match the size of the automobile containers. So those containers are a bit different. In the following slide, that is this slide, I have shown the covers of the monoblock batteries as well as the cover of the 2 volt cells. Now let us understand batteries. I would like to use an analogy to help you understand batteries and their performance in a better manner. I want you to imagine a person walking, jogging, running, and sprinting. Now, each of these activities requires a different level of energy and speed. When a person is walking, they stroll. When a person is jogging, they move at a slightly faster pace. And when they are running, they move even faster. When they are sprinting, they are swift. As you can see, the speed varies. The energy expended for each of these activities also varies. Similarly, batteries exhibit different performances and their performance varies according to the discharge rate. If you have a 100 battery and claim that it is a C10 battery, when I say C10, it is rated for a 10-hour capacity. You expect it to deliver 10 amps for 10 hours, which is 10 into 10 equal to 100 EH. Yes, that is perfectly fine. However, when you expect it to deliver 20 amps for 5 hours, it cannot maintain this for 5 hours because you are drawing more energy from the same battery at a faster rate. So here you will get only 16.66 amps for 5 hours. Similarly, when you expect it to deliver 33.3 amps for 3 hours, multiplying 33 by 3 and arriving at 100, you are making a mistake. You can expect a maximum of 23.9 amps for 3 hours. This is a characteristic of the battery. And similarly, you cannot expect 100 amps for 1 hour from a 100 battery, which is rated at C10. You can get only 50 amps for 1 hour if the battery is 100 at C10. Of course, a C10 rated lead acid battery can deliver 100 or even 1000 at a 1 hour rate. To get 100 in an hour, you need to have a 200 ampere hour C10 battery. Similarly, to get 1000 ampere hour in an hour, you need a 2000 ampere hour C10 battery. I hope this matter has been adequately clarified and you understand the relationship between battery capacity and discharge rate. The discharge current in amperes and the duration of discharge in hours do not form a linear relationship. As the discharge current increases, the capacity naturally decreases. This means you get less usable capacity at a higher discharge current. It's just like saying that if a person can walk for 5 kilometers, it doesn't mean they can jog for 5 kilometers. He may be able to jog for approximately 3 kilometers, run for about 2.5 kilometers, and if he's required to sprint, he can sprint probably for only about 1 kilometer. I mean, he can sprint only for 1 kilometer. Now let's move to the next slide. In the following few slides, we'll be talking about batteries connected in series, batteries connected in parallel, and batteries connected in a series parallel connection. Let me start with this slide where I am talking about batteries connected in series. Let me use three batteries as an example as shown. You find that the negative of battery 1 is connected to the positive terminal of battery 2 and the negative terminal of battery 2 is connected to the positive terminal of battery 3. So we have two terminals which are free. That is the positive terminal of battery 1 and the negative terminal of battery 3. Let us connect this to the load. This is what I've showed you, a series connection of batteries where the negative terminal of one battery is connected to the positive terminal of the next and the positive terminal of that particular battery is connected to the negative terminal of the next. In this example, there are three batteries, each battery of 12 volts and 100 Ah capacity. Many people mistakenly believe that if there are three 12-volt batteries, they should add up to 36 volts. And since each of these battery is of 100 Ah capacity, they should get a 300 Ah capacity. Well, it doesn't work that way. You will get only 36 volts and 100 Ah when you connect three batteries of 12 volt 100 Ah each in series. The voltage will increase while the capacity remains the same. So you have 12 plus 12 plus 12, 36 volts, and 100 Ah capacity shall remain the same. Let's see the example of a parallel connection in this slide. Here there are three batteries again, each of 12 volts and 100 Ah capacity. It's the same battery which I had showed you in the series connection of the previous slide. You find that the positive of battery 1 is connected to the positive of battery 2, which in turn is connected to the positive of battery 3. When it comes to negative, you find that the negative terminal of battery 1 is connected to the negative terminal of battery 2, which in turn is again connected to the negative terminal of battery 3. Here, you take out a cable and connect it to the load from the negative end and the positive end. So you have a set where you have three batteries connected in parallel, each battery of 12 volt and 100 Ah. What is the output you can expect? In this case, the output you expect is 12 volt 300 Ah. The voltage remains the same and the capacity is additive. Because these batteries are connected in parallel, the voltage remains constant, but the total capacity is increasing, and it is a sum of the capacity of each of these batteries. So you have 100 Ah plus 100 Ah plus 100 Ah, 300 Ah, whereas the voltage remains the same 12 volt and it does not become 36 volts. So suppose you want a 36 volt 300 Ah. What will you do? Let me explain how it is possible to get 36 volt 300 Ah from these batteries. Well, you cannot use three batteries and get that. You need the similar type of batteries, six more batteries. And this is how you will need to connect them. I've shown three lines of batteries with each line containing three batteries. You need to connect these batteries in series and parallel. In line 1, you have three batteries connected in parallel, which provides you 12 volts and 300 Ah capacity. The second line has three batteries in parallel, and again you have 12 volt 300 Ah capacity. The third line similarly has three batteries in parallel, each line giving you an output of 12 volt 300 Ah. After that, you connect these three lines in series. Next, connect the load to the negative end, which is line 1. And then you can connect the load to the positive end of line 3. You have the three lines of batteries connected in series to the load now. You will now have a voltage additive of 12 plus 12 plus 12, which equals 36. Because each line has a capacity of 300 Ah, the total capacity will now remain steady and you will have 300 Ah. I hope this is clear and it is evident that you cannot get 36 volt 300 Ah from three batteries. Here we have used a combination of batteries, totally 9 batteries, to achieve 36 volt 300 ampere hour output using a series parallel connection. In case you want to know more about batteries, chargers, battery management systems, or any related subject like EVs, you can always read my articles on Medium and Substack. You can also listen to my podcast on various streaming platforms, including Spotify, Amazon Music, Apple Music, and YouTube. I am active on LinkedIn and I am present on Facebook and Twitter too, but not very active on those platforms. My website is www.rameshnatrajan.in, and I also have a WhatsApp community and an email community where I frequently share updates and global news with all the community members. If you are interested in joining the community, please visit my website, access my contact details, and send me an email. If you are interested in learning more about batteries, you can access any of my books on Amazon. I have authored 3 books in English and 1 book in Hindi, and I shall be shortly releasing my 5th book next month, that is in August 2025. You can access these books on Amazon worldwide as well as on Flipkart. Thank you very much. I hope to release part 3 of my series 1 shortly. You can subscribe to my YouTube channel, and thank you for watching this video.